The Roman determination to supply their cities with water in abundance and of the highest quality obliged their engineers to design and build aqueducts of a magnitude as amazing as they are admirable. As the empire and its cities grew, these works reached astonishing proportions, capable of surpassing the best modern engineering. In the first category of Roman engineering, aqueducts were able to understand, thanks to the great aqueduct of Nimes, how a Roman aqueduct was designed and planned, the key to ensuring a water supply to a large city such as ancient Nemesis. And thanks to the aqueducts of Nimes, Téllez and Chelva, we were able to see that even very modest cities were equipped with large aqueducts, which confirms the idea that every Roman city should have a continuous and abundant flow of good quality water. The mysteries surrounding the subject of the aqueducts of many cities are innumerable. Unraveling some of them is a real challenge for archaeologists and modern engineers, some of them of such scope that researchers today cannot reach agreement between themselves. 200 kilometers north of Chelva is the amazing Roman city of Bilbilis, famous for being the home of the poet Martial. Bilbilis was a medium-sized city on the Roman road from Caesar Augusta to Complutum. Bilbilis had a singular characteristic. Located on a steep slope, it departed from the usual concept of a Roman city. Who knows why they chose to found Bilbilis in this location? Perhaps it is obvious. The views here are truly overwhelming, and its orientation is the best for that climate. Be that as it may, this decision presented an extraordinary challenge for the engineers who had to provide it with water. Because how could they get water to this height? Bilbilis is known for its numerous cisterns. About 20 cisterns like these are scattered throughout the city, all of them at different heights. There are several theories that explain the presence of so many cisterns. Some archaeologists have suggested the possibility that these cisterns were used to store rainwater. But how can one believe that the Romans drank rainwater after the efforts we have seen to transport water to Nimes, Nimes, or Téllez? Furthermore, in this region rain is very scarce. The rainfall is not much more than that of a desert, and the cisterns are at the high points of the slope. The cisterns would never be filled with rain. Bilbilis was not a great city like Nimes, but it was an important city. Of course, it was much larger than others we've seen, like Nimes or Téllez. The Bilbilis Theatre had a capacity of around 4,500 spectators. The thermal baths were also of a respectable size. But if it was not to store water, why so many cisterns? Let's look at one of them carefully. Here we have a cistern built with Roman concrete and waterproofed with the usual mortar. We can see the entry point for the water. But in these systems, there is no outlet down near the base. However, the exit hole can be seen slightly below the entry level. This means that this system cannot be emptied by gravity, and very little water is available between the difference in levels. Any container intended to store water has an outlet in the lower part. So this is not such a container. But if it is not a container, what is the purpose of so many cisterns? To answer this question, we are going to move to Italica, a city in the province of Baetica near Seville in Spain. Italica was an important city and had a fine aqueduct, measuring 35.5 kilometers in total, and according to studies of impeccable design and appearance. Near the city, this impressive group of cisterns was found. Here, we can see the water entrance channel coming from the aqueduct. And we see that just as in the Bilbilis cisterns, the water outlet for the supply is in the upper part. So this does not look like a storage container either. But if it is not a container, why is it so large? What was its function? We will recall the small sandboxes of the Nimes inspection wells. There, thanks to the recess at the bottom of the wells, sand and other suspended particles in the water were collected. The cisterns of Bilbilis, and in general those of all the Roman cities, have precisely this function, but on a much larger scale. Let's look at one of these in Italica. Water entered through the upper part and circulated through the cistern. Thanks to the large size of the cistern, water slowed down to almost nothing, allowing all particles in suspension to fall to the bottom by gravity. That is to say, they precipitated down, leaving the water clean of any solids in suspension. This process is called decanting. So these cisterns are, in fact, decanters. They were not used to store the water, but to purify it. The cleanest water is that closest to the surface, and for this reason the water outlet is at the top, just slightly below the entry level. Decanters are sometimes located at the point of origin of the aqueduct, but are usually located at the end, close to the cities. Their size is determined both in proportion to the flow of water that must be processed and by the quality of the water that arrives through the aqueduct, that is, the amount of sand and particles in suspension that the water carries. But in Bilbilis there is not just one single large distribution container, as is usually the case, but about 20 of them. Why is this? So we shall consider the highest of the cisterns found in Bilbilis. As we already know, the whole city must be below its level so that the water can be distributed with the help of gravity. But Bilbilis is a city that has a significant height gradient, meaning that there is a large difference in height between this cistern and the houses in the city that are in the lower part. The weight of the water exerts enormous pressure at the lower levels. It would be enough to burst any pipes, especially those made of lead. This the Roman technicians knew perfectly well. So to avoid this, they engineered a network of cisterns, more or less equidistant in height, so that there would never be a pressure higher than what amounts to 1 atmosphere, about 10 meters in height. In this way, when water reached the first cistern, it was decanted and remained at atmospheric pressure. Then by gravity, water was conducted to the next cistern, where it was decanted again and again without pressure. And so on, one cistern after another. It was an ingenious system of decanting and normalizing water pressure, which had to unify a complex system of water distribution to all corners of the city. This theory corresponds to the idea of maintaining a continuous flow of water and of permanent quality, the Roman standard for water supply to their cities. But let us remember, Bilbilis lies on a very steep slope. So the first cistern that had to receive water was at a very high level. How then to get water to it? Did the Romans have a source of sufficient flow and quality above this level? The answer is yes. About 10 kilometers to the north of Bilbilis is the Sierra de la Virgen, with important springs located above the necessary height and whose water could be collected and transferred through a canal at ground level to the outskirts of Bilbilis. However, a large depression divides these 2 points. To maintain the very small slope that the canal required, it would be necessary to build huge arches. Arches of up to 100 meters in height and over 1,000 meters in length. Arches of these characteristics would be absolutely unviable. So how to solve this problem? Roman engineers had substantial knowledge of hydraulics and of course knew perfectly well the principle of connected containers. This principle of physics tells us that containers connected at their lower level by a closed conduit will keep the liquid they contain at the same level, independently of the shape of the containers used. Using this principle, Roman engineers designed for Bilbilis what we know as an inverted siphon. An inverted siphon consists of a U-shaped structure in which, by the principle of the communicating vessels, water that enters one end will reach the same level at the other end. Following up on this possibility, we have recently found some remains on the other side of the depression. Surprisingly, far from Bilbilis and at the top of a steep hill, we have found a concrete Roman tank. On the hill of Bilbilis, the highest reservoir of the city, is exactly on a ridge that we can see from here. and it is 5 meters lower than the tank that we have just seen. Therefore, between both, there was a siphon that overcame the problem of the trough. Siphons are the least known elements of the aqueducts, although their use was very common and repeatedly employed in Roman engineering. To verify this, we will begin a journey throughout the empire. We will start in the northeast, in present-day Turkey. Year 330 BC. Alexander the Great controls his vast empire by dividing and entrusting power to his closest generals. General Lysimachus is given the governance of Thrace. Lysimachus orders the guarding of his treasures in the fortress of Pergamum. Located on a rocky hillside, this fortress will become an important city, capital of a kingdom, and a great intellectual center that will even rival Alexandria. Pergamum will have its own school of thought, and its library will be home to more than 200,000 papyrus scrolls. After the reign of several kings, Pergamum becomes a Roman domain. Pergamum had between 7 and 8 aqueducts of different eras. The so-called Aqueduct of Madradag was undoubtedly the most famous of them. This aqueduct collected water from several sources on the slopes of the Madradag, a range of mountains located more than 30 kilometers from Pergamum. The first source was 1,230 meters high. A pipe channeled the water to a second source located at an elevation of 1,158 meters. The flow of both sources combined, thereby increasing considerably. Therefore, from this point, the aqueduct builders decided to use 2 parallel pipes. These went on for 12 kilometers to a third source at a level of 650 meters. The increase in flow forced them to add a third pipe. The 3 passed together in parallel for 25 kilometers until reaching a decanter tank located at level 368 on Mount Hagios Georgios. In total, a route of 40 kilometers of buried pipes with a height difference of 862 meters. So they decided to use sections of 30 centimeter diameter bronze pipes. The sections were sealed with lead and connected between drilled stone ashlars. The whole arrangement being fixed firmly to the ground by long supporting bridges. Thousands of meters of pipes descended into the valley, resisting the enormous pressure and the great forces exerted by the water. They then crossed the valley floor, protected and suspended by arches. Finally, they ascended the opposite slope of the valley in order to reach the city of Pergamum at level 322. In total, a bronze siphon of 3.5 kilometers. The aqueduct of Madradag was already supplying water to the Acropolis of Pergamum towards the end of the 3rd century BCE, long before Roman rule. This is good data to certify that the main source of knowledge that Roman engineers possessed for the construction of their aqueducts was of Greek origin, and reminds us that the Greeks had already made prodigious works in earlier times. The siphon of Bilbilis would date approximately from year 0, estimated year of the city's foundation, some 200 years later than the construction of the Madradag aqueduct. It seems evident and proven that the Roman technicians already possessed great know-how in the design and construction of siphons at the time Bilbilis was built. The aqueduct of Madradag is of Hellenistic origin, but was extended, modified and maintained by the Romans when the city came under its control. This ability to acquire knowledge, expand and perfect it is one of the great qualities of Roman civilization. In this way, Greek engineering employing siphons was comfortably surpassed by the Roman technicians. We have excellent examples of this in Lugdunum, capital of the Roman province of Gaul Lugdunensis, the current and important French city of Lyon. Lugdunum was, for 3 centuries, the most important city of the Northwestern Empire. The enormous flow of water that Lugdunum required demanded the construction of 4 large aqueducts. All of them were equipped with impressive siphons. The most impressive of these aqueducts was the aqueduct of the Gia, known by the name of the valley from which it took water. The aqueduct of Gia had a total length of 87 kilometers. A canal that joined the chosen sources with decanter tanks that are still preserved on top of the hill in Lyon. 87 kilometers to cover a straight line distance of 42 kilometers. It was necessary to build 11 tunnels and some 40 sets of arcades, one of them being the arches for the junction with the siphon of Bonon, the largest of the 4 siphons employed by the aqueduct of Gia. This arcade has 250 arches that extend over 1,650 meters. And although it seems surprising, they were not the longest. Further on near the city, there was another one with 300 arches and 1,900 meters in length. These arcades were not built to overcome obstacles or valleys. Their purpose was something different. In front of us, we have the obstacle to overcome, the Valley of Bonon. On this side of the valley, the ground level is too low to get the water to the outlet tank that is on the other side of the valley. To reach the other end of the valley, it was necessary to increase the water pressure, increasing the height of the piping several meters above the ground. And this is the purpose of the arcades: to ensure the relative heights of the entrance to the tank and the siphon. Up there, the tank was joined with the siphon by means of 11 lead pipes. The purpose of so many pipes was to disperse the water pressure. The pipes were supported on ramps and covered with a good thickness of concrete. Concrete that helped resist the pressure. After 1,200 meters, the pipes managed to descend from level 313 to 191, where they joined with the venter. The venter was a bridge that allowed the pipes to remain elevated above the bottom of the valley, crossing roads, rivers, and even possible floods. The venter of the Bonon siphon measured 320 meters and was an impressive structure which is today still preserved to a large extent. These arches have a very peculiar wall covering, of great beauty, called opus reticulatum. In it were set individually carved small stones, in the shape of a diamond, and with alternating colors. The enormous numbers of arches manufactured were built in concrete, alternating with brick, and covered specifically with the opus reticulatum, a convincing proof that they were looking for beauty in addition to efficiency and functionality. This search for functionality and beauty led to designing these arcades with transverse arches across the water troughs in order to lighten the structure. However, the highest arches were blanked off. Why? When the siphon was working, the water pressure on the piping of the venter was enormous, transferring some violent forces to the arches. The bridge suffered enormous tensions and sudden movements. Perhaps the first time this occurred, the arches vibrated and moved so violently and menacingly that the engineers decided to reinforce the lateral arches of the watercourse. Aesthetics were therefore sacrificed in favor of safety. At the end of the venter, the water was pushed by the enormous pressure up the hill. This point was really critical. To the enormous pressure, sedimentation and the accumulation of sand was that the water could drag. This could cause the siphon to clog, leaving the aqueduct out of action. It was therefore necessary for the water to arrive clean at the siphon, free of sand and any particles in suspension. Lugdunum had large decanters at the city entrance, but they were positioned after the siphons, and there was no large decanter at the beginning of the aqueduct. So how did they ensure that the water was sufficiently clean to go into the siphons? In addition to the sandbox of the siphon entrance chamber itself, the gear aqueduct had about 1,000 inspection wells. Alternatively, these inspection wells had a small sandbox at their bottom. 500 sandboxes in total. The work of these 500 sandboxes along the entire route solved the problem of cleaning the water sufficiently, avoiding later problems in the siphons. After getting past the venter and pushed by the pressure, water ascended the valley slope, traveling another 1,100 meters and reaching the outlet tank at level 305. 8 meters below the level of the entrance tank of the siphon. From that point, water was conducted through the canal, now with hardly any pressure on the decanters located on the city hill. The impressive Bonon siphon passed across a 2,660-meter wide valley and surmounted its height of over 120 meters. The lead was ransacked from the gear aqueduct, most probably in the first years after the fall of the city, and almost no trace of it is left. The same happened with any metal in the aqueduct of Pergamum. Metals were very precious and coveted at all times, so looting was widespread. This explains why there has been no trace of any pipe that may have existed in the Bilbilis siphon. According to some calculations, the amount of lead needed for the construction of the gear aqueduct siphons amounted to an incredible 10,000 tons. And remember that the aqueduct of Gear was only one of the 4 aqueducts that supplied the city of Lugdunum. Luckily, some pipes managed to be preserved in other parts of the empire. Here in the Museum of Ancient Art, also in France, these wonderful specimens are preserved. Observing these carefully, we can see very clearly the technique used in their manufacture. The Romans built the pipes from a lead plate that curved around a wooden core in a tubular shape. Then the core was removed and the edges welded with a lead rod, leaving an oval cross-section and a visible longitudinal seam. The connection between pipes was made with a thick plug, which was also welded. We will move on to ancient Tarraco, capital of the Roman province of Hispania Citerior, for an interesting reflection on this issue. The general route of the Tarraco aqueduct is unknown. It is suspected that the water sources were located not far from the municipality of Alió, some 20 kilometers from the city. 4 kilometers before reaching the city, the aqueduct had to confront a trough of about 200 meters, where the construction of a siphon would have been the most appropriate. However, here we have some impressive and beautiful arches, the best preserved in the empire. At 217 meters long and with a height that reaches 27 meters, this is a costly and complex work that could have been avoided by building a modest siphon with much less effort. Why did the Romans opt for spectacular but expensive arches instead of for an effective and more economical siphon? Many of the works of the cities and their surroundings were sponsored by people of high socio-economic status. Such acts provided a good image and considerable prestige to the sponsor. The spectacle offered by some beautiful arcades in no way compares with the modest appearance of a siphon, which, although an admirable engineering work, has little in the way of aesthetic appeal. This place was close to the city and certainly next to an important road that communicated with Tarraco. So very probably, the construction of these impressive arcades was decided for their publicity effect and for spectacle. Another significant example of this are the awesome arches of the Aqueduct at Segovia, a beautiful city in the center of Spain. Virtually everything about the aqueduct in Segovia is unknown, including the date at which it was built. Yes, it is known that it supplied water to a very humble city, and because of the size of the channel that carried this water, we know that its flow was quite modest. If we remember the channel of Nimes aqueduct and compare it with the channel of this aqueduct, we will immediately notice the difference in flow rates of the two aqueducts. In any case, very close to the city, it was necessary to overcome a significant depression in the terrain. To move such a small flow of water, the construction of a pressure pipe, that is a siphon, would have been the most efficient and simple way. However, the construction of this marvel was decided upon. Built in large blocks of granite, which are held in place only by their own shape and weight, we are presented with a surprising and admirable design, reaching 28 meters in height. 24,400 stone blocks were used to construct 167 arches, 7,500 cubic meters of hard granite. The feeling of power and greatness that is aroused by a project like this is still evident in full today, despite being accustomed as we are to great modern engineering works. The propaganda effect and the desire to create a public spectacle are the reason for these colossal arches, as evidenced by the writing still preserved at the top, announcing its sponsor. The use of the force of gravity to drive water is the key to any Roman aqueduct. The water runs through the channels and goes through the siphons, pushed by its own weight. Therefore, cities must be built below the point where the aqueduct arrives. This also occurs in the Roman city of Uxama, city of Hispanic Celtiberia. But in Uxama we find something special and quite exceptional that merits a visit. Uxama had a certain importance in Roman times, largely because it was located in the important Roman road that linked Caesar Augusta and Ostorica Augusta, crossing the whole of Celtiberia. It was provided with water of excellent quality from sources that constitute the source of the Usero River. A pipeline of 46 kilometers was built that reached the city at a height only 12.2 meters lower than the level of the sources. Most of Uxama is currently still to be excavated and studied. Several containers similar to those of Bilbilis distributed water to the entire city. But some cisterns, among them this one, are above the normal level of arrival for the aqueduct. Why? On this hill, something unexpected and quite surprising was discovered. At the top of this hill, we found this large underground cistern that is actually a decanter. And the extraordinary thing about this decanter is that it is 40 meters above the level of arrival of the aqueduct. For some very unusual reason, part of the city needed to be at a higher elevation than the aqueduct and could not be supplied by it. The solution for this problem was to build a decanter at the top of the hill and distribute water from there to places where the aqueduct's water could not reach by gravity. But how did the water get to this cistern? The most plausible hypothesis is that it came out of the aqueduct itself and that a lifting system was used based on a treadmill, known today as a rosary wheel. A rosary wheel consists of a large wheel that drags a chain, equipped with small cups or similar objects that drag the water into a tube. In this way, part of the aqueduct's water flow could have been elevated to the decanter higher up the hill. The wheel could well have been pulled by animals, by wind, or perhaps by a combination of both, depending on the circumstances. Rosary wheels were also used by Roman engineers in mining operations to facilitate the drainage of water from the galleries. Many of the mining operations required the construction of important aqueducts, not only to evacuate water from the mines to the outside, but to take water from the outside to them. Gold mining required huge amounts of water for the removal of earth and the meticulous washing of the residue materials for the extraction of the gold. This may be surprising, because the usual image we have of aqueducts is that of water supply to cities. But aqueducts had many other applications, such as mining and agriculture. In the aqueduct of Arles, an important city of Narbonne in Gaul, we find a beautiful and original example. Arles was supplied mainly by two aqueducts coming from the nearby mountain range of the Alpilles. Both were of modest lengths between 20 and 30 kilometers, converging here, about 10 kilometers from Arles. This is the location where the two aqueducts unite, in a large distribution box, from which these two channels emerge. The objective of this box was the independent control of the flow of both channels. In these remains, we can see the impressive thickness of the waterproofing mortar, opus signinum, provided for these pipes. In this fallen piece, you can see perfectly the opus signinum mortar in the background and the well-polished vocel. And this plate is calcification buildup. Remember that calcification buildup is the precipitation of lime occurring during the hundreds of years of operation of the aqueduct. At this point, we can see how one of the pipes turned to the west to supply water to the city of Arles, while the other continued straight towards a steep slope. And on this slope, we can see the foundations of a construction whose obvious objective was to take advantage of the power of the water flow. From the remains found in excavations, we can reconstruct these facilities. An impressive flour milling complex comprising 16 wheels of almost 3 meters in diameter. The wheels were moved by the force of water as it ran down the slope. The movement was transmitted by various gears to the stone rollers that crushed the grain. It has been calculated that this mill could grind 3 tons of cereal per hour, enough to supply the needs of 80,000 people. In this documentary series, we have chosen the examples of the empire's aqueducts that we have considered most suitable from an instructional point of view. The main objective has been to transmit in the best possible way the fundamental and most important concepts of engineering in Roman aqueducts. We also wanted to choose some of them because they are not well known, thus allowing admirable works, many of them forgotten, to have the opportunity to obtain in some degree at least the recognition they deserve. But the empire has hundreds of aqueducts that we have not dealt with, some even more impressive in design and audacity than those we have seen, and that are worthy of being named. Like the aqueduct of Cherchel in Algeria, or that of Esch in Provence, and that of Metz in France, which are around 50 kilometers, or the one of Breven with 70 kilometers, and the splendid one of Fréjus with 45 kilometers, also in France. Many are around 100 kilometers in length, like Gades in southern Spain and Colonia in central Germany. The wonderful aqueduct of Aspendos in present-day Turkey, which dealt with the enormous pressure it faced in its final section, thanks to 2 intermediate towers and 3 contiguous siphons. All this on a large continuous venter made on large arcades. The great aqueduct of Cartago was supplied from several sources, the furthest one at more than 130 kilometers. It needed 16 kilometers of arcades so that the channel could maintain an adequate level as required by the city. Its colossal decanters were larger than a football field and simultaneously decanted some 60 million liters of water. The colossal aqueduct of Valente supplied water to ancient Constantinople. With more than 400 kilometers of channeling, it was one of the largest hydraulic works in the ancient world. In the colossal gold mining of Las Medulas in Spain, several aqueducts were built whose channels exceeded the incredible total of 600 kilometers in length. There, the force of water was used literally to dissolve the mountains. But surely the most spectacular supply system of all, as it could not be otherwise, was that of Rome. Rome was supplied at least by 11 large aqueducts, some of them with routes close to 100 kilometers. The 11 aqueducts in Rome supplied nearly 1,000 million liters of water per day to the city. The aqueducts of Rome are a spectacle in every way. Surprising and ingenious technical solutions, an immense number of tunnels and galleries, infinite and elegant combinations of construction with stone blocks and bricks, double channels, and even triple, all overlapping. And valleys crossed by kilometer after kilometer of arcades. We have reached the end of our episode. In it, we've learnt about new and awe-inspiring examples of water supply. We have understood the systems of decantation of water and the technique of the use of siphons as an alternative to arcades, and a unique and ingenious solution to overcome large valleys and gullies. And finally, we have seen how the use of aqueducts was not limited only to the supply of cities, but also for industrial and mining uses.